added was we could do variable change instead of constant change. And most people, by the time they get out of calculus, will tell you, if they got it, will tell you that calculus was easy, but that's also where they learned how to do algebra actually. Because calculus has a bunch of algebra, one simplest calculus step, and a bunch of algebra most of the time. And you get lots of practice for the algebra. So we're going to start looking at kinetics, which is that rate of change. So I'm going to do kind of a hypothetical reaction here for simplicity. So I've got some chemical A that reacts with chemical B to make C. And it takes 1 mole of A for every 2 moles of B to make 1 mole of C, just kind of making it up. So when we start this reaction, I'm going to put some amount of A and B in a container and let it start. And you've done this in stoichiometry, right? And in stoichiometry, you started with some amount of this and some amount of that, and you did the mathematic, and you made some amount of this, and you might have had some of that left over, depending on limiting reactant and all that stuff, right? You looked at beginning and end. Now we're going to look at the process. So lots and lots and lots of graphs in this chapter, and they're really important as far as interpretation, which is where I think you would. So down here, I'm going to put time, and these are kind of generic graphs, so I'm using the seconds. And over here, I'm going to put the amount of A. Now, we could do A in terms of mass or moles, but that doesn't give us much information. So almost always we're going to do the amount of material in concentration. And what do the square brackets mean? Do you remember? Chem 1, this is what we saw. Molarity. This is the concentration of A. And in this chapter, we'll pretty much do all concentrations in molarity. Didn't have to, that's just how most books do it, for simplicity. Could switch them over, we're going to do a lot. So this is going to tell us how the concentration of A changes over time. Moles of A per liter in the container. We okay with that? So, concentration of A, since it's a reactant, is going to start somewhere. Let's make up a number, starts there. That concentration we're often going to write as A naught. And all that is, and you put the O on the outside, the 0 on the outside of the inside, we're not going to differentiate. And all that means is the concentration at the beginning. And sometimes in the math, we'll leave the square brackets off just for simplicity, but it's still concentration. So as this reaction goes, what do you expect to happen to the concentration of A as this reaction runs?
Go down?
It's going to go down, right? Now you don't necessarily right now know the pattern it's going to go down. It's going to go down. We're going to learn very quickly things don't generally go to 0, but it's going to reach a point where it starts to stay the same over time. That'll be equilibrium. So, sloppily drawn, the concentration of air over time will something like this. Not using any numbers. So it starts out at some initial amount, and then goes down over time, and it eventually comes to a constant amount, the amount it stays at. And we're going to find out later that it doesn't just get there, it's actually going back and forth, but it has a balance and it stays the same all the time. That's equilibrium when it goes flat. What can you tell me about the concentration of B? And let me just change colors. What can you tell me about the concentration of B? It's going to go down twice as fast as A, because for every 1 A that's used up, 1 B is used up. Kind of logical? Sort of a trick question. What do we know about the concentration of B at the beginning compared to the concentration of A?
Or
not necessarily. It might be way more, way less, but we don't really know what the concentration of B will be. The concentration of B will be at the beginning, okay? Now, if it were all used up, it'd have to be double. But we'll just arbitrarily put B there. That's the concentration of B. And as you know, B will go down over time, but it will go down at twice the rate. So its slope will be twice A's slope at every point. Twice A's slope in the negative direction. And it'll come to some equilibrium amount that we don't know what that is yet. What can you tell me about the concentration of C? Depends on the structure, so I can't let's say that. Okay. C could actually start at some other number. We'll start it at 0. We'll assume we started with no C present. Not necessarily true. And C is going to go up, right? It's going to go up, and it's going to have some equilibrium value also. So if you look at our concentrations over time, all we know right now is that the reactants will go down and eventually flatline somewhere, and the products will come upwards and flatline themselves. Does that make sense? If you've taken calculus, you know that the slope of this line at any given point, or the derivative, is the rate. It's the rate of the reaction. So going back to algebra very quickly for some of us, you learned a long time ago you could take 2 points on a line, there, you could draw that, and this was the change in y, and that was the change in x, and slope was just a change in y over change in x. Remember that? If you haven't taken calculus, here's a 1-minute calculus introduction. And calculus is not hard, I promise. In calculus now we have a function that doesn't necessarily go linear, but you can still take a point and a point, draw that same sort of thing. This is the change in x, that's the change in y, and the average slope is still going to be change in y over change in x. And it would be represented, if I drew a line through those 2 points, the slope of that line would be the average slope between the 2 points. Does that make sense? The instantaneous slope, let me just change colors for slightly, is just at any point, it's the tangent line. And it'll be similar in slope, but not necessarily the same. And the closer your 2 points get together, eventually the instantaneous slope and the average become the same, collapse them together. And in calculus, we'll start to do this instead of delta y over delta x, we'll do dy over dx, which just means a super tiny change in y divided by a super tiny change in x. And that approaches some value, which is the instantaneous slope. Okay, again, you don't need calculus for this. All I'm going to do some calculus today to kind of show you where some of this stuff comes from. So looking at this particular reaction, or any reaction, we need to talk about the rate of the reaction. And just by convention, particularly in this class, the rate will always be a positive number. The rate of the reaction, I should say, will always be a positive number. And it's always going to be in units of molarity per second. So the rate will be how molarity changes every second. So if I said a reaction had a rate of 0.1 molarity per second, that means 0.1 moles per liter is reacted every second. Does that make sense? It's the rate at which the reaction occurs. It's how fast the concentration is changing. It does not have to be a constant. It may be a large number at the beginning and a small number at the end because the rate changes. Make sense? It'll only be a constant if it's a linear system, which we'll have some of those as we go. And I'll give you kind of a system for doing rates in a moment. So the rate of the reaction will be this overall thing. We can also talk about how the concentration of each material changes. So in this particular example here, let's talk about the change in the concentration of A over time. Will that be a positive or negative number? The rate of a reaction is always positive. The change in concentrations may not be.
Okay.
So A was a reactant, it's going to go down, right? So if I look at A's concentration at one instant and wait 2 seconds to look again, it'll be down, right? So it's a negative change. The change in A over the change in T will always be a negative number here, so it's drawn. What can you tell me about the change in the concentration of B with respect to time? Would it be positive or negative? It'll also be negative. How will those two relate to each other? Which will be larger, The change in A over time or the change in B over time?
Change B.
Change in B over time. And this confuses people in terms of just words. If I had to set those two equal to each other somehow, what do I have to multiply one of them by to make it a true statement? What's that? Okay. So I can say 2 times the rate at which A is disappearing is equal to the rate B is disappearing. Does that make sense? Or the rate A is disappearing is 1/2 the rate B is disappearing. Just algebra. Does that make sense? Both sides of this, by the way, right now are negative numbers. That's not the rate of the reaction. That just compares how one thing's changing with respect to another. So a way to think of it, we put Nick's money. So every second, Nick's gonna give us $1. I like this system already. I'm gonna give $2. Crap, I don't like this system. Okay? And she's gonna get the money. So how is his money changing every second? What's that?
Decreasing by $1.
He's decreasing or losing $1 per second. How's my money changing? Decreasing or losing $2 a second. And her money? Increasing by 3, right? So if we were to compare our rates, you can double his rate to equal mine, or half my rate equals his. Does that make sense? What if I want to compare their rates? What do I multiply by to get one to equal the other?
Multiply by 3. Or negative 3. The opposite.
Right. 3 times his rate, but negative would give you her rate. Does that make sense? Or negative 1/3 of her rate will give you his. His rate's negative, hers is positive. By multiplying hers by a negative number, you make it a negative number. Make sense? And here's what's weird. What if they compared my rate to hers? So the change in Davis's money over time came up with the same letter. Last name over time. My money, her money, are rates. What would I have to multiply one of them by to make them true?
Negative 3/2.
On which one?
Yours.
Okay, he's suggesting negative 3/2 of mine. Does that make sense? What do you mean? Well, ignore this number. Which one of these is larger?
Yours. No, hers is what?
Hers. So you have to multiply mine by a number greater than 1, ignoring the sign, to get it to be the same as yours. Does that make sense? Think of it as normalizing. If you divide mine by 2, you get it back to his, because his was 1, so it's a good reference point. Hers is 3 times that. Or, this is true, or just by algebra, I can scale hers to that. Does that make sense? But we want to be clear. We're looking at changing concentrations that's related but different than the rate of the reaction. The rate of the reaction is going to be kind of this normalized thing. And your book's going to give you this little formula that I'm not going to run the board because it will mess people up. Because it's a gimmick. They're into this whole thing about A, B, and C, and it's the ratio of these. No, because it depends on what the question asks. Be very careful with that. I don't like, this book's the only one I know that does that. When we actually start talking about our reaction rate, though, so rate of reaction, here's a formalism. Rate of reaction will always be defined in terms of the reactants, only the reactants. Because we're looking at how the reactants change. So rate is rate equals, this is very important, K times the concentration of each reactant, using our model here, to some power, X and Y. We currently do not know what those powers are. They are not the coefficients.
And what's K?
K is the rate constant. This is the rate of the reaction. This is the rate constant. These are the concentrations of the reactants.
What's the rate constant based on?
Give me a moment, we'll get to that one. Because there's a weirdness that's happening. And X and Y are powers. Usually, they're nice powers, like 0, 1, 2, 3, or -1, -2, -3. half, but they don't have to be. But most of ours, at worst case, will be halves. Most of the time, they'll be integers. All right? And we will find those. We'll talk later about where they come from. The rate constant is based on the system itself. So, what kind of units would the square brackets have? Molarity, or moles per liter, right? What were the units for rate? Molarity per second, right? The units on the rate constant will shift to fit the powers. So, using the same reaction, these are things that could happen. I'm just doing examples. Let's say, experimentally, we found out that the rate law for this reaction is rate equals K times A to the second power, B to the 0th power. Anything to the 0th power equals what? 1. What's the exception? 0 to the 0th power equals, damned if I know. It's an indeterminate form, depends on how it's done. But we'll ignore it. So I don't need to write the B to the 0th there. I just wanted to show you it's in the equation. It's just often, if it's raised to the 0th power, you won't see it, right? So what are the units for the reaction rate always? Molarity per second. So what will the units for K be, the rate constant, in this example? Test questions, all sorts of things. What would the units for a rate constant be if this were the rate law? So, the units for A would be molarity per second, right? But we're squaring that. So what would need to go here to make the units right? What units? What times molarity?
Seconds over moles? Or seconds over molarity?
I'm sorry, I lied about something. Sorry. Oops. What are the units for A? Molarity. I'm going to keep them in molarity now, but you could break them down to moles per liter. Those will sometimes, for simplicity. A is molarity, right? So what are the units for K in here?
1 over seconds times molarity.
In this case, 1 over molarity times seconds. Because they have to cancel out one of the molarities and they have to produce the seconds, right? Does that make sense? So we haven't put the number in yet, we'll find that. But the units for K in this example would be 1 over molarity times seconds, also written as molarity times seconds to the -1 power. Which is more common how you'll see it. You okay with that? We will say, if this were the rate law, we will say that this reaction is second order in terms of A. It's a second order reaction in terms of A. And since A is the only one showing up here, it is a second order kinetics reaction.
Can you repeat that?
It's second order in terms of A, as its exponent. And since A is the only one that matters here, it's a second order reaction. Remember that B is sitting here if you want to see it. What is this reaction in order of B? 0th order, which means B doesn't affect the rate. And so what's the overall reaction order here still? 2. It'd be 2 plus 0. Just like you did in algebra. Make sense? Yes?
It wasn't 0. It still continues to order reaction.
No. I'm getting it, let's kind of do a quick example. If that were there, and we wouldn't write the 1, but if you want to see it, this reaction now is second order in A, first order in B, third order overall. This is the third order reaction, second order in A, first order in B. Does that make sense? Yes, because that's what they did in algebra, if you remember. The order of a polynomial was the sum of the coefficients. So if you had 3x squared y to the 4th, what order polynomial is that? 6th order. Second order in x, 4th order in y, 6th order. It's the same idea here. All right, let me change it up because important statement, let me say a big one. Rate laws are determined experimentally. You cannot guess at them except in very special cases. Rate laws have to be determined experimentally. So what if this were the rate law? Rate equals K times A, B. Those are brackets, just on my bed right. This reaction is what order in A? First order in A. What order in B? First order. What's the reaction order? Second order reaction. What would the units on K be? Units on the rate constant.
1 over molarity times seconds.
Same as last time, because it's still getting rid of molarity times molarity. It's just different chemicals. So K here would have units of 1 over molarity times seconds. We're good with that? Change it up. What's the overall reaction order here? Third order. First order in A, second order in B, third order overall. What are the units on the rate constant? 1 over molarity squared seconds. So just gonna verify it. That would be molarity. That would be molarity squared. This has to be molarity per second. So 2 of those cancel 2 of those, producing the right units. Kind of make sense? Rates and all these can be in other units other than molarity, but we will not do those. We'll stick to molarity per second, which is pretty common. How do we get an actual rate law? How did I tell you determine rate laws? Experimentally. So they're going to give you, they being me, experimental data, and from that we're going to determine the rate law. We're going to do this in the lab too. Just in the lab, it won't be as nice. I want to qualify, there are 2 different styles of this. The numbers can be really, really nice where you can just look at it and go, oh, it's that, which is fine, it's useful. And then they can be less pretty. Don't always assume one or the other. Make sense? So let's start with a nicer reaction. Anybody happen to know what that compound's called that has its own name? That's ozone. Ozone, under the right conditions, can be forced to kick over to just the oxygen molecule. And to balance this, we get that. So this is the decomposition of ozone. Is ozone good or bad?
Good.
If anyone ever asks you is something good or bad, it depends on where it's at and how much there is. It's one of the really bad social things. I listened this morning to my office mate, he's a biologist, and he had a former student from a different school come in. And I watched, because he had so much trouble not saying anything inappropriate, he kept trying to bite his lip, but she'd say things like, pork is bad for you. And he'd go, why do you think that? And she'd give an argument. And he'd go, well, yes, if this. Pork can have some really bad microorganisms, and particularly worms, if you don't treat the animals and you don't cook it. If you cook it completely, that's not an issue, right? And then she told him how rice was now made out of plastic because it's GMO. And about 10 other things, okay? Good and bad is a relative term. Moderation is usually better. Potassium chloride, which is one of the most common salts, is on all over the surfaces in here. If you have high blood pressure and your doctor wants to lower your sodium levels, okay, they will tell you to go to the store and buy potassium chloride, it's fake salt, and put it on your food. It tastes roughly the same and it doesn't have the same effect. What happens if you inject potassium chloride into your veins? Dead in seconds, stops the heart. Potassium chloride is fine if you're ingesting it. Really bad if you're injecting it. Okay, so you get that good bad thing. Ozone in the stratosphere is good. It takes the gamma rays from the sun, basically runs a version of that reaction, and protects that energy from getting to us. If the ozone were to deplete too badly, we're toast because the cancer levels will go off the charts on a scale we've never seen because gamma rays are deadly. No. Ozone good. You can go to Walmart and buy an ozone generator for your house. It reduces the dust, it does, okay, because it ionizes particles in the air and it's good for that. It cleans the air. Why do you not want to do that?
Well, we breathe in O2. So if it purifies the oxygen.
It doesn't remove enough of it, so that's true, not enough. But ozone is mildly toxic to human, extremely toxic to large birds like parrots. It's sold to parrot owners to reduce the dust. Birds produce a lot of this dust off their fur. To protect it, it kills parrots, and it's highly toxic to grass. So it wipes out vegetation and most avian species. Atmosphere good, down here bad, but tons of people buy them. But it's that idea of not knowing what we're doing. Sidetracking, sorry. Okay, ozone. So in this reaction. So in the lab, I run an experiment, and this is called the initial rate method. Because most chemical reactions, the rate changes over time, we will find a way to measure it at the beginning and kind of use that average to indicate. So in this particular, we're going to run 3 experiments. And when you run these, you can choose what concentrations to use. And if you pick the numbers to be nice, it helps. So in version 1, I'm going to start with a concentration of 0.00150 molar ozone. The second one, I'm going to double that, 0.00300 molar. I'm picking numbers just so they're nice. And I'm going to double that again, 0.00600 molar. And when I do that, I'm able to measure the rate for each one of these. And the rate for this one is 3.08 times 10 to the negative 8 molarity per second. This one is 1.28 times 10 to the negative 7th molarity per second. And 5.03 times 10 to the negative 7th molarity per second. So we can tell as we increase the concentration of O3, our rate got faster. That kind of make sense?
So how did you just pull these numbers?
That's experimental.
Okay.
I did 3 runs. I controlled, I wrote it down, but whoever controlled the concentration of ozone in the reaction, and then they measured the reaction rate at the beginning.
Okay. Cool.
Visually, I can look at this. So here's the first thing to do. If I want to write the rate law for this, it has to be in the form of rate equals K. There's only one reactant here, right? The ozone. So K times the concentration of ozone to some power. I don't know what that power is yet. Does the O2 show up in the rate law?
No.
No. I want to make a big point about that because the next 3 chapters on equilibrium, the products will show up. In kinetics, it's only reactants because they control the reaction. I need to find out what X is. So I can pick any set of data. Let's take the second and the first. So the second one, looking at the second one, I know that the rate is equal to, the rate is 1.28 times 10 to the negative 7 equals K times 0.00300 to the X power. I just plugged in the values because I knew the rate and I knew the concentration. I didn't know K or X. That's for the second one. And you'll see why I pick it in a moment. If I do the first one, I get 3.08 times 10 to the negative 8 equals K times 0.00150 raised to the X. Are we okay with that? And now, by algebra, I can divide one equation by the other. I picked the bigger one on top just because it makes the numbers nicer for most people. So ignore this for just a moment. When I divide this by this, K cancels, right? And what is that divided by that? This is 2 to the X. Because 0.003 divided by 0.0015 is 2 raised to the X power. Let's put this in a calculator. Before you do, let me just point something out. You'll have your calculator. If I write this, that's 12.8 times 10 to the negative 8 divided by 3.08 times 10 to the negative 7. Sorry, negative 8. What's that roughly going to be?
4.
4. All right, let's get the real value real quick. If somebody was to type it in for me. It's going to be about 4.
Is negative 8 again?
What's that?
Yeah, negative
Are you putting negative?
Well, they'll cancel out, so they really don't matter.
Is it good, right?
Just one.
Yeah, it's a negative.
Well, it was 1.28 into -7, which you can type that if you wanted. I just wrote it in the same exponent so you can see easily. You're
Oh,
going to
you-
get
okay.
4.1558. So what we get?
Not at first.
Stick on my answer. If I was seeing the algebra here, so you don't have to type all the things, will save you a lot of time. Get right in the steps, you'll see it. So if this were 4, let's just call this 4 exactly, for a moment, let's lie. What is x? 2. You can kind of see that, right? We okay with that? X is going to turn out to be 2 here. This is experimental. 4 would be a nice number. How would you solve this algebraically now if you need to solve for x?
The log.
We'll take the log of both sides. Which base log do you want?
10.
Hey, I don't know.
Or 2. Log these two separate.
Could log those two in on your calculator, so
Which?
doesn't matter which one you take. You can take base 10 log, you can take natural log, you can take base 2. The problem is your calculator only has base 10 and base e usually, right? I'll take base or natural just because that's what we use for everything else. It doesn't matter. So this is whatever logarithm you pick to this side equals whatever logarithm you pick to that side, and then what? By the rules of logarithms, the x can come down in front. Remember that? I just saw a few say that. The log base b of x raised to the y is equal to y times the log base b of x. And then I can divide. So x equals the natural log of 4.155 divided by the natural log of 2. If you use base 10 log, you get the same answer. So type that in for me and tell me what you have. I want you to do it because I want to be sure we know how to do that. Raise your hand when you have an answer. I can pick it up.
2.055.
Or you can say out loud. Yeah, 2.055, which is fundamentally 2 is normal error, right? The numbers are nice, you can look at them. If not, you have to do the math. But this tells me that x was 2. So this is what order reaction? Second order reaction. So there's our rate law, but now we need to find k. How can I do that? Plug in any set of data and solve for k. Now if it's experimental, you may need to do all of them and take the average, but they're going to be very close to each other. Does that make sense? So I'm going to take this one here and solve for k, knowing that x is 2 now. So I'll square that and divide it, I'll get k. I'll square that and divide it and get k. I can do the third one, they'll be very close to each other. But when I do, k turns out to be 1.27 to the -7th divided by 0.003 squared. And when I did this one, k was 0.01411 repeating. I'll do the next one just to see what we get. 3.08 to the -8th divided by 0.0015 squared. I get k is 0.013688. And to do the third one, just to check, 5.03 to the -7th divided by 0.006 squared is not that. .01397, and since this is experimentally, I'll take the average of them. So that plus that plus that, 5.3. And I'm going to get an average K value here of 0.0139. What would the units be? concentration squared, and what were they? The units? 1 over molarity times seconds. Or you'll normally see it written like that, molarity seconds to negative 1 power. That's the rate law. The rate law needs everything filled in. It needs the K with the units and the exponent. This now tells you the rate at any concentration. So now you can put in any concentration of ozone and find out what the initial rate of the reaction would be. The initial rate, because it'll change over time. The rate will decrease over time. But that's how it starts at. Does that make sense? The numbers can be really nice, they can be ugly. This example I picked here only had one reactant, which makes it nicer, but it also lets us do other things. You can have multiple reactants, and we'll do an example in a minute. But let's look at single reactants first. So, can I erase this? So, the math I'm about to put up here only applies to a single reactant. It doesn't apply if you have multiple reactants that make an effect, but for single. And does anyone have a heart condition? So do I, don't worry. Okay, don't have a heart attack, don't make them about those calculus at. You don't have to be able to do calculus, you don't need to repeat this, but for those who had it, this will help them see what happened here. The rest of you, just, we'll see it later.
Thanks.
It actually will make some sense, hopefully. If I have, let's just look at A goes to B for simplicity. My rate law is going to be something like rate equals some constant times the concentration of A to a power, right? And we're measuring the rate of this in terms of how the concentration of A changes over time. We're good so far? So, in algebra terms, that's how you write it. If that were a 0, what's that tell you about how the rate is affected by A? It's not. The rate is always a constant. The rate is whatever K is, and the concentration of A doesn't affect the rate. That does happen at times. Does that make sense? What this means is how A changes over time is just equal to a constant. Yes and no, hang on a second. It's going to be flat. Does that make sense? So, switching over to L on calculus speed, don't freak out on me. I'm going to get rid of the brackets for simplicity, but that's dA over dt. That's the change of A over time is equal to a constant. And for those of you who've had calculus, that means the integral of dA equals the integral of k dt, which means A equals kt plus c. We okay with that? Calculus speed. And c is just this constant we have to find. So when t is 0, c is just whatever A started at, right? So the concentration of A at any time is equal to the rate constant times time plus whatever the concentration was of A at the beginning.
What's that y am I supposed to be?
It's y equals mx plus b. So what is the order of that reaction? So for a 0 order system with one reactant, and this chart I'm about to make is on your formula sheet. A 0 order system means the change in concentration of A over time is just a constant, which means the concentration of A at any time is equal to, I lied, sorry. A is going down, right? A is decreasing?
Yes.
Those are negatives. Because A is decreasing over time. Negative K, so negative KT plus A naught. This is called the integrated rate law. You do not need to derive it, it's on the sheet, but it helps to see. This is how the concentration changes over time. So this tells you how the rate goes over time. This tells you the concentration is a function of time. Totally different functions. This, you can plug in a time and see what the concentration is. But wait, if you order today, there's more. Let's say that the change in A over time depends on time, all right? And it's still decreasing. So it's equal to negative K times T. So now the rate differs as time goes along. The rate will decrease as time increases. We okay with that? Switching over to calculus mode. This is dA dt equals negative KT. The integral of dA over, oh, I lied to you, sorry, I lied. I had to stop doing that. Depends on concentration of A, not time. dA over A equals integral of negative K dt. This tells you that the rate depends on A. You've seen this equation before, you just don't know it. It's one of the most important equations. All right, calculus people, what's the integral on the left side? What's the integral to the left side of this?
Is it really dA over A?
dA over A. It's how A changes and divided by A. This is the natural log of A, and since A can't be negative here, we don't worry about it. So natural log of the concentration equals negative KT plus C, and when we do our substitution, we get the natural log of the concentration equals negative KT plus the natural log of A naught. This is a first order system. Where the change in concentration of A over time is equal to decrease in the concentration of A. And the integrated rate law is the natural log of the concentration equals negative KT plus the natural log of where we started. Anybody recognize that equation? That bottom one, the natural log equation. It's similar, but it really shows the thing. By algebra, I can subtract this from both sides, right? So I'll get the natural log of A minus the natural log of A naught equals negative KT. Logarithms say I can put these together as the natural log of A divided by A naught. What's on the right side? And how can I get rid of the logarithm? I can exponentiate using base E. So A over A naught equals E to the negative KT, oh right, which means A equals A naught times E to the negative KT. And you've seen that before in algebra, and calculus, and biology, and Chem 1. That's exponential decay. That's how every natural population goes, that's how your bank account goes, that's how the temperature in the room goes. It controls almost all natural processes. So here's a way to think of it. If I'm going to put a bunch of rabbits together, assuming they're of the right gender, and I want to figure out how fast we're going to make new rabbits, how fast I make new rabbits depends on how many rabbits there were, right? How the number of rabbits changes over time depends on how many rabbits there were. In this case, it's exponential. Make sense? And it produces that. Exponential decay covers radioactive decay for anything, bacterial growth. Like I said, anything involving compound interest. Temperature by Newton's law of cooling will cover all this. It's incredibly important. First order equations follow that. This is the exponential form, and you've probably seen this before, or heard of it at least. Last version we're going to look at this is second order. And of course, these can get very complex. We're only going to go for one reactant in a second, and then anything else we'll do other ways. So I could say the way A changes over time could be negative K times the concentration of A squared. And now it's the second order, right? So in calculus speak, this is dA over a squared equals negative kt, sorry, negative k dt. We do the integrals, this side becomes negative 1 over a, that side becomes kt plus c, which gives us negative kt plus c, which gives us 1 over a equals kt without the negative plus 1 over a naught. And that's the second order relationship. So if the change in A over time is controlled by a second order of a single reactant, our integrated rate equals 1 over the concentration at any given time is equal to kt plus 1 over the initial concentration. And those are on the formula sheet, but I don't want them to just be like boxes here, at least to see how they came, even if you're not doing the math on the intermediate, which is fine. What people have the most trouble with on this is going back to graphical analysis. So I have, let's look at zeroth order. I have this situation. What could I plot on the x and y axis to make this a line? And this is kind of what you did in lab the other day.
Well,
Hang on.
polarity of A is on the y-axis, and T is on the x-axis.
If I plot time on the x-axis and the concentration of A on the y, I'll get a straight line, which is redundant because all lines are straight in over space. And what can you tell me about the slope of that line?
It's negative K.
It's the opposite of the rate constant, right? And what can you tell me about the y-intercept?
It's the well,
The original concentration.
It's the initial concentration. So for a zeroth order system, if I plot time and concentration, I'm going to get a line. It's going to be a line with a downward slope. The slope of this line is the opposite of the rate constant, so you can just take the slope and change the sign and you have the rate constant. And the y-intercept is a naught. You okay with that? Once you see this, these are the super easy questions. Because you can look at what's plotted in the zeroth order. You can get the slope off the graph, and a naught, and then you simply write the rate law for this will now be rate equals k, which you got off the graph, times the concentration of A to the 0th power. So we don't write it. Thoughts? Lots of graphs. Let me do this one here. So, still talking 0th order. If I plot time here and rate here, what will that graph look like?
Isn't it just a linear line
Yeah, flat line.
plus with a positive slope?
A flat line.
It's a flat line.
Is it fine?
The rate is constant. The rate in this case does not depend on time. The rate is, so the rate would be some positive number. It'd look like that. And the value right here in y would be whatever that k value was. Does that make sense? The rate equals k. This is y equals mx plus b. M was 0. B was k.
Okay, I get it.
First order now. Let me start with the bottom one. So for a first order reaction, if I plot time here and rate there, what would the graph look like?
Now it's gonna look a lot of the pause. Actually, it'll probably look like the first graph on the.
So I want to start with that one might confuse yours. Let's see.
like this.
Let me do this first before I get to that. Let's do this because it's gonna make it harder for you. If I plot rate versus concentration of A, what would that look like?
So,
Correct, what time are we? I realize that. Very quickly. The rate equals negative Ka, something like that. And we'll continue this on Tuesday. All right.